Okay, so let's begin with the numerical part, right. So, we sort of try to understand the 3D picture of the conical flow, right, and we saw that you know how some of the phenomena, if we have a cone at an angle of attack and so on and so forth, right. So, let us see how in order to solve for the properties around such a surface, which is a cone, right, and then you have a shock wave. So, to solve for these numerically, say, how do we take account of that? We have, for example, vertical singularity. Okay, how would that be taken care of by the governing equations? The governing equations are again the continuity, momentum, and energy. Okay, so how do we make sure that these governing equations are actually giving us what we try to see physically in the couple of last lectures? Okay, so let us see. What we'll first try to do is exactly find out how the governing equations, right, give us the vertical singularity, show that we have each streamline has a single value of entropy, and so on and so forth. Let's do that, right. Now, so along a streamline, therefore, each streamline basically has a single value of entropy, right. So, therefore, there is no change in the entropy across along a streamline. So, along a streamline I can write, right, I write that as a total derivative. So, therefore, okay, let's call this as say 1, okay, and therefore, for steady case, okay, steady flow, okay, we get from 1 right, we just have the convective part. So, for steady case it boils down to this. Okay. Now, what we will do is write this whole thing in spherical coordinates, okay, because gradient S therefore becomes okay, and okay. So, if I write 2 in terms of spherical coordinates, so gradient S becomes this and V becomes this. Let us just make sure we understand what this means. Okay. So, what we are seeing here, V basically in here has these 3 components. Now, hopefully you are aware that this E r, E theta and E phi are unit vectors, right, unit vectors, normal squared, whatever. So, these let me just I am going to write it like this. Okay, E r is synonymous to I j k, and it is analogous to the I j k in Cartesian coordinates. Okay. So, basically we have r, theta and phi directions, okay, in which direction we have taken unit vectors, and the velocity components in those directions is r, theta and phi. So, again here, so now gradient of S is basically the change in S, okay, is the convective change in S. So, you see del S del r in the r direction, 1 by r del S del theta in the theta direction, 1 by r sin theta del S del phi in the phi direction. So, let us just sort of make sure we understand what this means. Okay. Okay, so, okay, let us say that this is what we have. Okay. Okay. Now, this is x, okay, and this is y. Okay. This is x and this is y, and okay, in this particular case, so x, y, and z. Okay. This is the 3D picture. I am trying to sort of draw this right. Okay. And on, so therefore, my, if I do this from this vertex, if I draw this line here, this is my cone. Okay. So, essentially, okay. So, this becomes my cone, right, cone surface. Now, let us take any point say here. Okay. Let us take say any point over here. Okay. This point here, and we will drop a radial line from here, okay, this, which makes an angle theta, right, with the x axis, and we will also drop a radial line from this vertex till here. Okay. This is r, okay, and this angle is phi. This angle is phi, right. This is something we know from before, right. So, then in that case, now along this direction, right, we take a unit vector and call that as E r. Okay. Then along this direction, we take a unit vector and call that as E theta, and in this direction we call a unit vector and call that as E phi, right. Make sure, so this makes sense. So, this is something that I think hopefully if you look at those 3D diagrams, it will it will register something, it will register in your mind. Okay. So, essentially, so this is what I'm talking about. So, in this particular case, so in here if I take the total velocity at this particular point. Okay. So, I have a velocity component. So, I instead of I could have here, for example, if I was looking just at this particular plane x, say okay, let me say okay. So, at this particular point, let us call that as p, right. At this particular point, now the velocity could also be v like u, v and w, which is in the x, y and z coordinate system, which is the same, but if I, instead of taking the components of that in the x, y and z direction, if I take the components in the r, theta and phi direction, that is when I get v theta, v phi and v r. Okay. So, that is what it means, and this is the change. Okay. This is the change in r, theta and phi directions essentially. So, if I have a point goes from one point to the other. Okay. So, if I have a point say this P, okay, was at some location here, was originally at some location here, and it moves from P dash to P. So, you can see that here, okay, the theta, the phi and the r are all different, is not it? The theta, r, and if I were, let us say, do this, okay, here. So, you can see that the theta, r and phi are all different. Okay. So, say P, it moves from P dash to P. Okay. This is the convective change in the entropy. So, it moves from P dash to P. If it does that, then there is a change in the entropy, because there is a change in the radial direction, there is a change in the theta, there is a change in the phi, okay, which is what is represented here. Which is what is represented here. Now, why is it not just del s del theta? Now, this is the math part of it, the geometry part of it is easy to find out. I would request you to do that or consult a very basic standard text, and this should make sense. Okay. You do that once and then just take these equations as they come. Okay. But if you have not understood this by now, okay, maybe it is high time just go and take a very standard text, look at polar coordinates and spherical coordinates and cylindrical coordinates, and just make sure you understand why these terms come in here. Okay, you have to do that once. As long as you know, that is fine, you understand. This one, you need to memorize this. Okay. So, for a steady flow, we can write this, and in the spherical coordinates, this is how we would write. So, therefore, I will write this equation 2, okay, equation 2. So, then we will write it like this. Here, let me write equation 2 as, so we have equation 2 in spherical coordinates, right. Okay. So, basically, okay, we have, so if you look over here, V dot, it's a dot product, V dot delta S, gradient S. So, we have these two vectors here, these are two vectors, we need to take a dot product. Okay. So, that is all. I mean, E r dot E r is 1. So, that is what we get. So, we get V r. Okay. Why don't we write it here itself? Why don't we write it here itself? So, if you look at these two terms over here, so what we get is V r del s del r, okay, plus V theta by r del s del theta, okay, this, then plus V phi r sin theta del s del phi, right. This is what we get. Now, from here, okay, from here what we know is that along, this is still the conical nature of the flow is still maintained, and the property along a radial direction is constant, right. We had talked about this earlier. So, in the cone at 0 degree angle of attack, for the cone at a certain angle of attack as well, the property along the radial direction is still constant. Okay. So, that does not change. So, therefore, the entropy along the radial direction does not change. So, if I am moving from point P dash to P, okay, the entropy will change with respect to the change in theta and phi only, it will not change with respect to r. Okay. So, let me call this equation as 3, okay, and then taking that out. So, basically what we will have is that this term will go. Okay. So, we will have this as only this term and this term, right. This 3 is basically left hand side of equation 2, right. This is the left hand side of 2. Okay. So, therefore, equation 2 becomes basically V theta by R del S del theta plus V phi by R sin theta del S by del phi equal to 0, right. Or what we can write here is del S del phi, okay. I can write that as minus, okay, V theta, okay, by V phi sin theta del S del theta. Okay. So, this equation, okay, this equation as we see here. So, this is basically an expression for the entropy change, okay, an expression for the entropy change on a streamline, right. This is, and what we can see here, that it is connecting the entropy with the physical parameters theta and phi. Okay. This theta and phi is what? This theta and phi now. So, therefore, if I if you sort of recall the way we were looking at the streamlines, okay, if you remember this. So, let me just quickly sort of remind you what I am talking about. Okay. So, okay. So, we have a say cone like that, right. We have a cone like that, and if I look here, right. So, this is a if I if I project this onto here. So, I will basically look at a circle, right. So, if you remember, right, that we had streamlines like this. We had streamlines like this coming over, right. So, then now these streamlines, if I project it here, they were nothing but points on the points on this projected plane, right. So, therefore, in here, okay, now this is if say the point moves from P dash to P, there is a change in R theta and phi, but what we can see here is that my change is happening only with respect to theta and phi, because the flow is still the flow properties still are constant along R directions. So, which means that in here, okay. So, here what we have written, the entropy change in terms of the velocity parameters, okay, velocity v theta and v phi. Okay. So, let us see how this if I were to look at this change just in terms of changing the physical parameters, okay, theta and phi, just the geometry. So, this here 4 is a relationship between the change in entropy with respect to the velocity components. Okay. So, if I do this, so say that total say ds, okay, change in the entropy you see what I am trying to write over here, which is different from here. Now, the way we got equation 4 is from here. So, we use the equation of the not exactly the physical equation of a straight line, but the fact that the entropy is single valued on a particular streamline, which means this, right. So, therefore, when I have this particular streamline, so you can think of this, when I say it is moving like this, going from P dash to P, right. So, if you are looking at say this is say P and this is P dash. So, basically I am going from this point to say this point here, which are the same streamlines. Okay. So, therefore, there is a change in theta and phi when I go from here to there, okay. But there is no change in the radial direction, the property still remains same. So, we use this equation and we wrote out the change in the property in the entropy with respect in terms of the velocity and velocity in the theta and phi directions. Now, what we try to say is that if I were to look at it another way, that the entropy change when it goes from say P dash to P, and I look at it say as a change in theta and phi. So, what I am writing it as that the change in total change in entropy, okay, is a change in entropy in the theta direction, okay, and a change in entropy in the phi direction. That is what it amount to, isn't it. So, this you can write as ds in the theta direction and this is ds in the phi direction. So, these are the two directions in which it is changing, it is not changing. So, I do not have a ds in r direction, we do not have that because it is constant, but we do have this. Okay. Now, on a streamline, ds is what? There is no change in the entropy, right, because it is single valued on one particular streamline, it is single valued. So, it is equal to this. Therefore, from this expression what we can write, okay, I will write this as say 1. Okay. So, therefore, okay, from 1 what we get, okay. So, what I will write here is d phi by d theta, okay, which is equal to okay. Let me call this as 2. Okay. So, all I do from here is write it. So, what I look here is the relationship, is the change in the theta direction and the change in the phi direction of entropy is given in terms of change in the theta and phi itself. Okay. Equation 4 was giving us change in the you can write it here also actually the change in the theta and phi direction if you look at this in terms of the velocity components, whereas here we have the change in the theta and phi directions of entropy in terms of the change in phi and theta itself. Okay. So, therefore, using again, so if I were to use here, okay, if I were to use equation 4. Okay. So, therefore, what we will get is that okay. So, now what I have here is the d phi d theta okay, in terms of v phi with the velocity component. So, what is this giving us? Okay, if you were to think of this as an x y coordinate system, okay, x and y coordinate system, this would be like dy by dx, which is the slope. So, this equation is essentially giving us the slope, okay, the slope of the streamline in the theta phi plane, which is the projection, here, the theta phi projection here. Okay. So, what this is giving us is the shape of the streamline on this projected plane. Okay. And I do not know if I mentioned this, right. This plane is called the cross flow plane. Okay. This plane is called the cross flow plane, because if you look at this, you have all sorts of if you remember, right, we had this was for the angle, for the zero angle cone, right, zero angle of attack cone, and for something like this, or for something like the at a certain angle of attack, we had something like this. So on and so forth, right. We had all sorts of things. So, this plane is called the cross flow plane, and the velocity that we had talked about, right, which was this v theta v phi in this plane is total velocity. This is the cross flow velocity, and when this goes to 0, then you have a stagnation point, right. Okay. So, so now therefore, let us so therefore, equation 4 and equation 5. Now, what equation 5 is giving us, okay, is the shape of this streamline in the theta phi direction, in the theta phi plane. Okay. So, in the theta phi plane, 5 gives us the shape of the streamline, and 4 gives us that for a change in that theta and phi, what should be the change in corresponding entropy. Okay. So, armed or equipped, okay, with these two equations. Okay, let me write this equation one more time. Okay, just let me write it here for I want to make a statement here. Okay, so this is ds, or yeah, let me write it like this: ds by d phi is equal to minus del S by del theta. Now, this is our equation 4. Okay. Now, if you look at both these equations, so here I have v phi by v theta and v theta by v phi. Okay. The question to ask here is, which is fine, which is always fine. So, this gives us a shape in terms of these velocities, and this gives us a change in entropy in terms of these velocities. So, numerically that is it, should have no problem, right. Is there any issues here with this? Okay, the hint is that in here in this space we had a stagnation point, if you remember. Okay. These are the two stagnation points, and this was also a point of vertical singularity, right, if you remember, right. So, what was this stagnation point? The stagnation point was when this is equal to 0, it means it is a stagnation point, right. Then this becomes a right. So, this velocity, this is the cross flow velocity. When this becomes 0, what we get is a stagnation point, right, makes sense. So, therefore, if in that particular therefore, now 5 and 4 are fine, 5 and 4 are fine as long as we have a finite v phi by v theta, but what if v theta and v phi are 0, right. So, the exception is that when if we have a stagnation point, right, what we have is a stagnation point. Okay. Okay, and this becomes indeterminate, right. So, this becomes so basically v theta by v phi or whatever, okay, is indeterminate. Okay. These equations, therefore, if you look at these equations 4 and 5, therefore, they are allowing us more than one solution for the entropy value for the entropy at a particular point. So, therefore, this is going to allow us, okay, for multiple values of the entropy, okay, at a particular point, okay, which means that we have what? We have vertical singularity. Okay. If you remember, right, vertical singularity meaning at a particular point we have more than one value of more than one value of the entropy. Okay. So, this is now numerically being shown. So, if I look at this equation here for a time being, for just for a second, forget that this v phi and v theta are velocities, just consider them as some arbitrarily random value, something is just a number, just think of it as a number. So, if I look at that, if I see that this, then the ratio of these numbers v phi or v theta, something, they are not velocities, it is just some arbitrary value that I am taking. If each of these goes to 0, then I have an indeterminate equation over here. Okay. I have an indeterminate equation over here. So, and in this particular case, however, this v theta and v phi corresponds to the velocities in the theta phi directions. So, what we will therefore get is a stagnation point, and hence at a particular point we will have more than one value of the entropy, which means we have multiple values given by 4 and 5, and hence which is the vertical singularity. So, therefore, the vertical singularity is being shown by the equations that we are using. Hence, this is a correct representation, right, of the flow around a cone at an angle of attack. Okay. That is the whole sort of gist of it. Okay. So, now what we will do is do this task of, you can of course look this up, you can kind of look this up at from any standard book, but I kind of want to write this down, okay, write this down and give you a feel for this as to how these will look. Okay. Now, let us go ahead and do that. The governing equations in our usual okay. So, these are our governing equations for 3D. Okay. Inviscid, adiabatic, compressible, right. So, this is our flow, and what is our this is our continuity equation, right. So, okay. So, this is the continuity equation as we know it, okay, in our usual coordinate system. If I write this in spherical coordinates, okay, what does this look like? Okay. So, the way I will write it is in the way I will write this is all the changes here, okay, in terms of the change in the radial direction. I will write all properties like that. Okay. So, this is it, and okay, if you look at this, Okay. Okay, and I am going to call this equation as 4. Okay, I am going to call this equation as just call this as 4. Okay, so this is my continuity equation, and this is in the spherical coordinates. Okay, so then we have the momentum equation. Okay, I will write the momentum equation here. Okay, so momentum equation recall that is 2. Okay. Now, this is something that I will now write in the r, theta and phi directions. Okay. R, theta and phi directions, and let us see this momentum equation. Okay. So, then the momentum, okay, this is r direction. In the r direction, so that looks like this. Okay, which is okay. Okay, so this is the equation in the r direction. So, I am going to just cross check that v theta by r, v phi r sin theta, that, and yeah, looks okay. All right. Okay, so this is in the r direction. So, then we have the theta direction. Okay, then we have the theta direction, which looks like this. So, like I said, I am writing all the parameters with with respect to r on the left hand side. Okay. So, I do that. Okay. Okay, that is the theta direction, and finally, in the phi direction. Okay, finally, in the phi direction, okay, which is okay. Okay, plus okay, the handwriting is really bad. That's it. Okay. So, okay, so that is how the momentum equations look like in the r, theta and phi directions. Okay. And along with this, okay, so along with this we also need the energy equation, right, and the energy equation. So, the energy equation is okay. So, total enthalpy, okay, so which is equal to total velocity at one point, isn't it? Okay. And we call this, and along with this we will along with this, of course, we have the equation of state and the calorically perfect gas relationship. So, which is right, this is the equation of state right. So, these are basically our equations. Okay. So, we wrote down, you can see here. So, this continuity equation, then equation, the continuity equation, this is in the spherical coordinates, then the momentum equations in r, theta and phi directions, okay, energy equation, okay, and the equation of state and perfect gas equation. We have these, and well, I think at this point I will kind of briefly go over a method, okay, which was, I guess, right at the beginning when people started doing this, and I will just illustrate briefly as to how this method will proceed, how we can do this, how we can solve for the properties here. So, let us look at these equations. Now, if you look at these equations here, so let us see what are the unknowns that we have in all the equations that we have written. So, one is this V r, okay, then we have V theta, okay, we have V theta and we have V phi. So, that makes it 3 unknowns. What else do we have? Okay, we have the pressure, okay, so that is one, and what else do we have over here? So, then again we have the enthalpy and we have the temperature, isn't it? So, if you look at this, if I were to write that down, so our total unknowns, okay, are our V r, V theta, V phi, okay, then pressure, temperature, enthalpy, and what else? Okay. Oh, and the density, forgot about that one. So, let us look at the density. Yeah, sorry. So, there we go. So, the density. Okay. So, therefore, so we have these 7 unknowns. Right. We have these 7 unknowns which need to be calculated using these equations that we have here. So, basically so this is 1, 2, 3, 4, 5, 6, 7. So, these are the relationships etcetera we will use to calculate. So, 4 to 8 we will use equations to solve for our unknowns, and this is a numerical procedure. I will sort of, it is not possible to sort of clearly explain in a board. You have to write a computer program, and if you have a brief bit of idea as to how to progress, I think you can do that. But unless and until you write a computer program, it is difficult to explain the whole thing, but I will try to go over the gist of it. And it is important that some of these earlier methods are also given in these references. I would like to sort of write those down for you, so you can take a look at it. Okay. Okay, so one reference. Okay, if I were to sort of briefly write this. Okay, some of the references. Okay, if you look at the references, for example, by Kopal. Okay, this. And this is tables of supersonic flow around yawing cones. This is tables of supersonic flow, okay, around okay. So, this was the this was basically analysis tech. It's a tech report. Okay. This is some of the like really early methods. Okay. This is one reference. Another reference is another reference is Joseph Sims, actually. Okay. So, tables of supersonic flow around right circular cones at small angle of attack. Okay. So, again this is tables for supersonic flow around right circular cones, okay, at small angle of attack. Okay. So, you can write that this is say okay. So, well, these are all sort of before I was born. So, yeah, so it's slightly old, but it's nice to know from where things have started. Okay. And the method that I will talk about, okay, the method that I will sort of explain is basically towards right at the beginning. It's given by Moretti. Okay. So, you can look at the paper yourself and go through the details of it. I will just make a brief gist of it. Okay. And this guy, so Moretti. Okay. So, which is inviscid flow field okay, about a pointed cone okay, at an angle of attack. Okay. And this one, AA journal, Okay. Okay, so I think what I'll do is basically stop here. We'll pick it up from here to in the next lecture actually, and so all of these, I mean, you know, all of these are kind of old because these are old before my, you know, earlier before I was born. So, however, this is a method that I will show you, and I also picked up a paper which is more recent, okay, which is more recent, and it's got some nice pictures, okay, numerical results basically, and you know, I'll give you the reference and you can take a look at it, okay. And of course, you yourself also can look at other references and more sort of recent work in this if you're interested, and do some recent work yourself. Okay. So, I will stop here and we will sort of go over this you know, briefly as to what this, how we will be able to calculate, you know, 7 of these properties. Okay. So, we will stop here. Thanks.